For this video, I'll be working through question 2 of the 2017 Scholarship Physics exam. Question 2. A mass of 1 kg is dropped 2 meters onto a sticky platform mass of 2 kg. The platform sits on a spring constant of 1 times 10 to the power of 2 Newton per meter. So before we start, we'll just do some labeling because I want to solve this algebraically. Just to show the easier way to do it, because you can do it numerically, but whatever. Mass equals 1 kg, and I try to do everything algebraically. Big mass equals 2 kgs. This is going to be the velocity of 2 kg block. 2 kg. This is just for me to like track, and this is going to be velocity of 1 kg block. Sweet. So, by using appropriate conservation laws, show that during the collision between the mass and the platform, 2/3 of the gravitational potential energy lost by the mass is converted into heat. State any assumptions made. So before I even start, this sort of question, this is a mechanical impedance question. I'll post in the description like a really good application to this, but it's a really interesting topic. And the tricks that we'll use here, you can use for a lot of questions. So I'm going to split this page up. I'll grab a line down here. If you were to try and attempt this question, it took me like, I'm writing the answer that I got, but I used like a pad paper. So when you do this exam, stick your hand up and ask for heaps of like spare paper to like write your answers, because there's barely enough like room to write your answer neatly on this, unless you're some sort of savant and just know the answer beforehand. But anyway, so the two things we're going to use: momentum, P equals mv, and energy, E equals half mv squared. Your initial momentum is equal to the final momentum, assuming conservation of momentum, which you can, because we're just going to look at that little instant when they collide. So just the instant as soon as they collide. If you look at the collision a little bit longer, you can't really say momentum because you've got conservation of momentum because you've got an external force, which is gravity. But just for that momentum, that collision instantaneously, you can sort of say it does. Right. Little mass times little velocity. Initially, this here is the only thing that's moving, is equal to the little mass, and now they stick together. So we got little mass times the big velocity plus the big mass times the big velocity, because these two smash together, stay together, and move down a little bit. So that is our formula there, and then we could just factorize this. Little mass plus big mass is going to be equal to times the velocity. So that is just this factorized. So I'm going to rearrange this for, we'll do it, little v is equal to mv over bracket big M. How do we do this? Little m plus big M. And what else do we got? Is that technically correct? No, this is big V. Big V, what am I doing? That is big V. And bracket little m plus big M is equal to little mv over v. So I know how to write this because, well, I know to write this because I've already solved this on a big sheet of paper, but I fiddled around with some stuff because you'll see soon that I had to figure it out pretty quickly. So I've written it there. So energy comparison, because we've done the momentum comparison, now we need to do comparison. Initially we have half little m little v squared, and now, so that's the initial energy. We have half little m big V squared plus half big M big V squared. Now what are we going to do? So we're going to try and compare apples with apples. In other words, we're going to try and get rid of the big velocity. So we're trying to rearrange our way out of having the big velocity. In other words, we'll use these formulas up here, substitute them into this energy comparison, because what we're trying to do is we're trying to look at what happens to the energy. So we're going to try and look at, once this is all solved out, whether our initial energy is equal to our final energy or whether there's some discrepancy, because that's what it's asking for. So in other words, if we factorise this here, we get, and I'll get rid of all the halves as well, so you times by 2, little m, little v is equal to mv over big V, v squared, and I missed out that squared up there. Right, no, that's right, I've skipped a step. What am I doing? That's not equal to that. That is equal to little m, because I'm going to pull these little m's out, plus big M over times v squared. What am I doing? Right, now we're going to substitute out this for that. So this is where, like solving on a piece of paper and then coming back to it can help, because you would have got to here and you would have thought, oh, I'm going to rearrange one of these momentum formulas to stick in here, which is normally always what you do, and we'll use this technique all through this paper. So that is going to be equal to this here times v squared. So little m, little v over big V times v squared. You can see that we can cancel this and this out, and we can cancel the little mass and the big mass out. Yes, we can. So we get v squared is equal to v times big V, but no, we don't want to try and compare apples with apples. So we're trying to get rid of, we're trying to compare the velocities that are the same, or energies that are the same. So we'll get rid of this. We can substitute in this here because we already rearranged, so we can substitute that in for that velocity there. So we get little m, little v over little m plus big M. And now we'll move that to the other side, so we get big M plus little m v squared is equal to little m v squared. So now if you put the numbers in, we get 2 plus 1 v squared is equal to 1 v squared. I'm leaving out the units because whatever. In other words, 3v squared is equal to v squared. Now we got a comparison. In other words, the energy beforehand is 3 times as much as the energy afterwards. In other words, we've lost 2/3 of the energy. So we'll put thus, since 3v squared is equal to v squared, 2 over 3, so 2/3 of the energy is lost. Energy must be lost to heat. Lost to heat. We'll just put assuming inelastic collision. Inelastic collision. Which it says it's a sticky. It says it's a sticky platform, so it must be the case. Right. Next question. Show that the maximum amount of additional compression that occurs in the spring is 0.473 meters. So we're going to break down this question, and we're going to have a look at what's going on. When this block hits this platform, it has energy half mv squared, but 2/3 of that energy is lost. So it has kinetic energy, but that was gained from the potential energy. We had that different distance, so we could say that is mgh. But the trick to doing this is, I'll write up here, fg is going to be fs. So initially, this spring is holding up this mass. In other words, you've got the mass, the big mass of the block. Mg is equal to, This is the force of the spring, so it's just K. But what I'm going to do is I'll draw a wee picture over here. I'm going to break down some distances. So here's that 2 meters. Here's that platform here. Here's a spring. Oh, that's a terrible spring. But what we've got is, if this platform had nothing on it, it would be up here somewhere. If we can see that. So we've got a distance from here to here, which we'll call this delta X. Now, when this platform here, the 1 kg, hits this one here, it goes down somewhere to here. And this is going to be called, we'll just call this X, this distance X. In other words, we'll look at the final energy. So your formula for the energy that's stored in a spring is just half K X squared. But when these two blocks are on top of each other, the distance is X plus delta X. So we'll put X plus delta X, because it's that change from the equilibrium position with nothing on it, squared. So this is the final energy. It's easy to look at the final energy, and that is equal to the initial energy. So we've already discussed that. We've got that little mgh over 3, so the energy given to us by that little block. We have, when that little block lands on there, it goes down and finishes somewhere down here. So that distance from here to here times, or that loss in gravitational potential. So we've got mg x plus delta x again. And then we've got that loss in gravitational potential from that big block just moving down to the new resting position, which will just be big M little g x. Right, so I'm going to expand out this quadratic equation here, because this is quadratic, so we'll, I suppose, unfactorize it. So we've got half kx, not kx, just bracket k, scribble it out, x squared plus 2x delta x plus delta x squared, and this is equal to, I'll just put mgh over 3 plus, I'm going to smash this out a bit, mgx plus mg delta x plus mg x. Right. Go back up to here. We had mg equals k delta x, because initially that big block was just in equilibrium. This is going to help us a little bit later to try and unfactorize some things. And those things that we're going to unfactorize, or not unfactorize, I'm going to talk about, to cancel out some terms. We can rearrange this delta x, because I want to try and get rid of that delta x, equals m g over k. There we go. And now we're going to substitute this in here for as many of the delta x's as we can, and that'll get rid of a whole lot of stuff. So what we're going to have is we're going to have half k, what will it do? I'll expand this bracket out. So we've got kx squared plus, what are we going to have? We had 2 there, so we get rid of that half. We're going to end up with kx, but I don't want that delta x, so I'm going to substitute in this mg over k plus, what do we got? Half k big M squared g squared over k squared, because this here is squared, so I'm going to substitute in this here squared, and you'll see we'll do some cancellation soon. That is equal to mgh over 3 plus mgx gx plus, what has got, mg, is that, yeah, mg squared, no it's not, it's just mg, big M, oh it is g squared, because we had this g over here, over k, because we've substituted this into here, and now we just get plus m mgx. Right, so if we do some cancellations, I'll whiz through. We can get rid of that, get rid of that, get rid of them, get rid of them, and we'll rewrite this out. So we're going to have half kx squared plus mg, oh that's m squared. Oh, hold on, did I cancel some stuff? Yeah, I'm going to cancel this xmg. I'm going to cancel these fellas too, because they're on either side, so I'll just cancel them out. So I'm going to get m squared. Am I got a half in there as well? Yeah, no, we'll put that in mg squared over 2, because I cancelled those two k's, I put that half underneath. And now I'm going to minus stuff, so I'm going to move everything to one side, so we've got this one big ass quadratic equation. And that is going to give me 1 mgh over 3 minus mgx x minus mg squared big M over k equals 0. Boom. Everything we have except for x. We've got all the big M's, we've got the little m's, we've got gravitational force, we've got the spring constant. So if you plug this, well, if you expand this out, you'll do this on your scrap paper. 50 x squared minus 9.81x plus 1.924 minus 6.54 minus 1.92, that should be 1.92, that should be 4, equals to 0. And then you put this into your calculator solver, because it's faster. X is equal to 0.4728. Hey, we solved it. Or 0.2766. And there's a minus. Thus, compression equals 0.473 meters. Right, we'll move on because we've already used up a whole lot of time. Right, calculate the amplitude of the resulting vibration. So we've got a new equilibrium point. There's no how you spell it, whatever. Is going to be equal to little mass plus a big mass times gravitational constant times, or just times 9.8, 1 kx. Just same as above. So we got this new equilibrium point. And in other words, if you can solve this, we've got everything here except for x. So this x is equal to 0.294 meters. So this is our new equilibrium point, and we're going to try and find out what the total unstretched length is, and then it'll be the difference from there. No, it won't be. It'll be, so we've got this. This is a new equilibrium point, but we've gone 0.473 meters down from the old. Yeah, okay. So here's the point we're going to be oscillating around, and we need to find. Okay, here we go. Top / unstretched. Stretched. So we have 0.473 plus just mg over k, because that was the old point. So originally it's here. This distance from here to here is just mg over k plus the 0.47, which will get us down here. That'll give us the total, like, stretching amount, if that makes any sense. So it's how much it can, that's like the total, I suppose, the amplitude. It's not really the total amplitude, it's how much it stretches. And then we're going to oscillate around this point, 0.294. So this is equal to, m is just 2g, you can plug it in, 0.666 meters. Now, the amplitude is equal to the max, so we'll just put max minus the equilibrium, EQIL, and that is just equal to this minus that, which will give us 0.3 0.72 meters. How do I know how to do this? It's because you find out your new equilibrium point, and then you find out how much it stretches, and then it's just the difference. And that's pretty much that. Right, show that the total energy at the bottom of the motion is equal to the total energy at the top of the motion. So, bottom, we have E is equal to half K, and we've got X plus delta X squared is equal to, we have X, we have delta X, there's X, delta X is there, no it's not, here it is, this is delta X, X is 0.47, and that is equal, yeah, so this here is delta X, yeah, and then 0.47 is X, that is equal to 22.378 joules. I don't want this to go over too long. Top is equal to the gravitational, hold on, so mg2 plus x plus delta x. Right, why have I done this? This is the total energy of the smaller mass. So it had that 2 meters. Then, so this is the energy it had to get all the way to the bottom. So we're just going to use that energy to go all the way back up to the top again. So it had that 2 meters height. It had the energy that it went down to the bottom, and then it's that little extra delta x as well. And we're going to add that to half the energy that was stored in the bigger mass when it was just at equilibrium point, which is half K delta X squared, which is just equal to 22.378 joules. Look at that, they're the same thing.